In this video, I'm going to work through example 1.55 from our text. That's in section 1.4 concerning biconditionals. So if you haven't yet, read through section 1.4. This example will come up. I'd suggest you to read through it, but if you get stuck understanding what's going on, come back to this video and take a watch. So let's see. Here we're given two open sentences, P of n and Q of n. This has a similar flavor to other examples and problems from this for these sections. We want to find out when a combination of these is true. In particular, we want to know when is the biconditional P of n if and only if Q of n true. For which integers n is that true? So it makes sense when solving a problem like this to first figure out when P of n is true and when Q of n is true. Then we can use the truth table definition of this to figure it out. So we'll ask those questions. When is P of n true? And when is Q of n true? That's where we'll start. So what does it take for P of n to be true? Here we have n minus 1 squared. N minus 1 squared is always greater than or equal to 0, right? Even though I square a negative, it's greater than or equal to 0. So n minus 1 squared is always greater than or equal to 0. I want to know when it's equal to 0. Well, that'll only happen when n minus 1 is equal to 0. So when is P of n true? Only when n is equal to 1. So that is P of 1 is true, and P of n false for n not equal to 1. So that's some good information to have. What about when is Q of n true? Well, here we have a linear function equal to 0. Linear functions only have one root. So again, there should just be one value of n that makes this true. Or is there not even one, right? There's one real number that makes this true, namely 3/7, right? This tells me n equals 3/7, but 3/7 is not an integer. So Q of n is false for all integers n. And now we want to know when is the biconditional P of n if and only if Q of n true. So I'm going to go one more level here. I want to know when is P of n implies Q of n true. And I also want to know when is the converse of that true. Q of n implies P of n. Remember that P of n, if and only if Q of n, is the same as saying that P of n implies Q of n and Q of n implies P of n. So that is P of n implies Q of n and Q of n implies P of n. So both of these have to be true in order for the biconditional to be true. So that's why I'm going down to this next level. Once I figure out when these are true, I'll take the conjunction of them and I'll have my answer for the biconditional. So let's see. Let's investigate when P of n implies Q of n is true. So in order for this to be true, I need whenever P of n is true, I need Q of n to be true. That's all I have to check, right? So P of n is true only when n equals 1. So I really just need to consider this implication when n is equal to 1. When n equals 1, right, P of 1 is true, and I want to make sure, is Q of 1 true? Well, no, Q of 1 is false for all n. And so in that case, this cause-effect relationship doesn't exist, right? P of n being true does not necessarily mean that Q of 1 is true. So this is false for n equals 1. False for n equals 1. Now, anything other than 1, my hypothesis won't be true, right? P of 0 is false, and it doesn't matter if Q of n is true or false. It'll still be true that P of n implies Q of n. And so for all other situations, P of n is false. And so P of n implies Q of n is true for all of those. So true when n is not equal to 1. How about Q of n implies P of n? Now my hypothesis is Q of n, and my conclusion is P of n. I want to know is whenever Q of n is true, does it follow that P of n is true? Well, Q of n is never true, and so this is true. There's nothing to check. There's nothing to enforce. True for all n. So now I take the conjunction of these two, P of n if and only if Q of n, and I need both of these to be true. So this is true when n is not equal to 1, and this is true for all n. So P of n if and only if Q of n is true for all n not equal to 1. All right, that's it for this video. See you next time.